Okay, so good afternoon. I hope you started. Of course, you are doing the regular study towards the exam. You might have seen the flavor of the questions, right? So the first question you saw, I mean, that was in the quiz, right? Anybody got the answer? Okay. As expected, right? So now, sample paper I have given to you, right, on the WhatsApp. Some people may not have even seen that also, right? I know. So basically, that is last year paper which I put, Of course, I can create tons of such things. Good thing is that this morning I created a question paper for you. Beautiful paper. So I should tell you there are only 4 questions. First question is average. Average person can do it. Second question, uh, what is that question? I'm just recalling. Third question is very easy also. Any average person can do. So if you are doing all the regular things, you can do it. The second question is, yeah, a little bit confusing. And last question is, so one part of the question is very easy, the last, and second part is difficult. So again, probably there is some Ramanujan or some genius sitting in the class. I want to figure it out who is that person. So you see, 4 questions. So I hope any questions about the, because 4 questions are sufficient to know who you are. Your competitive programming ranking is not valid here, right? So, see, I'm always telling you that about that, but there is a reason why I always tell that, right? So let us see who can actually get. So as I mentioned, in most of my exams in the last 30 years or so, there is only one person who was able to crack 100% in all the exams. Okay, so I don't know who is going to do that. So, and that person, as I mentioned, is very successful person. So I think if I want to find out who is that good person. Each of you have a lot of potential. थोड़ा सा मति भ्रम है, so you can actually focus. You can do great work, right? So with that, let me start. So if you have any questions about, see, I will be available on WhatsApp anyway. If you are having doubts or something, you can ask. I think nobody is using WhatsApp, right? People are not asking any questions there because they're all busy with competitive programming. And I know towards the end of the exam is ek din pehle, right? You will say, okay, what is there in this course? So I will observe that there will be peak view, number of views on the YouTube just before the exam. Okay, and that's also fast forward, right? You don't have enough time to actually do everything. So you see, it's all about श्रद्धा. जिसकी जितनी श्रद्धा है लाइफ में वो उतना ऊपर जाएगा, right? कम श्रद्धा, you will achieve less. ज़्यादा श्रद्धा, you will achieve more, right? So this is very, very important thing, right? Anyway, so I was talking about, so more or less this theoretical computer science, I will be able to cover most of the things before so we have 2 more lectures, including today. So there are 3 lectures total. We should be able to cover most of the stuff by that time. And after that exam, and I think you have on 2nd May or what? Yeah, 3rd May, right? 9:30 to whatever. So it's only 2 hours exam. Frankly speaking, all those 4 questions you can do in 1 hour. And so you are left 1 hour, it's like buffer for you to think. Okay. So that's why I've given 2 hours. So it's very standard that I have been using since last 30 years or so. 4 questions will enough to judge you. I don't have to prepare long question paper, right? So, okay, so I think, yeah, so that's all about question paper. So now we were looking at finite automata. So as I mentioned, in theoretical computer science, the summary is there are only 4 kind of machines: finite automata, push-down automata, linear bounded automata, and Turing machine. And we have to understand few basics about this. At least in this course, we will cover few basic things. Okay. I already talked about finite automata, DFA, deterministic finite automata. I gave you a couple of examples and so on. So given a DFA, you have to identify the language. Given the language, you have to identify the DFA. And I think some of you might have started doing the homework. If not, probably because I have not changed the homework from the last year, somebody might have taken solutions also from there, or they might have printed and then probably they'll look at it towards the end of the exam, right? Whatever. Again, jiski jaisi shraddha. So I think, see, if you do it regularly, it will be good, because if you do it yourself, you will learn how to actually find out. Given a language, how to find the DFA. Given a DFA, how to find language. Okay, this is a very important thing. At least this much you should know. Okay, so now the second machine that I'm going to talk about, this is also finite automata. It is known as non-deterministic finite automata. So in DFA versus NFA. So what is there in DFA? DFA, for each input symbol, we have a deterministic choice where to go, right? Only one choice where to go. Here, after receiving one input, you have multiple choices. So which one to take? Which path should I take? That is really interesting. And in terms of computational power, both NFA and DFA are same. They are equivalent. That means they both accept regular languages. Okay. So they accept same sort of languages. In fact, towards the end of the lecture, I will show you that any NFA can be converted into DFA. So I'll give you an example how an NFA can be converted into a DFA. So non-deterministic finite automata can be converted into deterministic finite automata, right? And also, one very important thing I should mention, that many times when somebody asks you to find out the finite automata for a given language, normally what people do, first they construct NFA, because that's easy to construct. And once you construct NFA, you can easily construct DFA using the algorithm which I am going to tell you. This is a normal approach, because construction of NFA requires less efforts as compared to DFA. Okay, you might have seen that while constructing DFA, very important condition that you need to keep in mind, that for every symbol and for every input, there should be a transition to follow, right? That is a very important condition in the DFA. In NFA, that condition is relaxed. So basically, you are having much more flexibility. Okay, and another very important flexibility that we have in NFA is that I can provide delay. When we are reading some input, tape will not move, or it will not move to the next symbol, but the state will change. So that can be achieved using what is known as lambda transition. So this is also very important difference between NFA and DFA, right? So let me start NFA. Again, I'm thankful to Professor Bush, because I'm using his slides with permissions, of course. So non-deterministic finite automata. So let us look at this NFA. Alphabet is having single A. So when this is the start symbol, now for that given A, I have two choices, either that path or this path. So the question is, what should we do? Any idea? So now, how do we do computation? So there we have two paths, one on the top, another one on the bottom. Any idea? Which path to take? Yes.
Accepted. Then no, we'll check one path. If that is accepted, then okay. If it's rejected, then go to another path. So we backtrack and
Not backtrack. Actually, what we do here, we go to all paths parallel. So once we start from that first state, so one path is you go to Q0, Q1, Q2. Another path is going from Q0 to Q3. So two parallel here will happen in parallel. Computations will happen in parallel. Okay, and whichever path we go, input is consumed, and you reach to the final state in whatever path. At least one path is required. Then you accept the string. That is a basic philosophy. Okay. So you run in parallel. So there are multiple choices. You run each choice will give you one computation, right? Every time. So there is a sort of a bifurcation of the computation is going on in parallel all across, right? And then you see which path will give you the answer. So let me show you here with examples. Okay, so two choices. And one important thing, you can see that there is no transition from Q2 or either Q3 also, right? And in one path of computation, in fact, there is no accepting state. In one path, there is one accepting state, right? This is the key difference. Now, first choice, if you read if you read string A, so one choice is you go to Q1 and Q2 you accept. So all input is consumed and the string is accepted in one choice of computation, right? What about the other choice? Second choice, input cannot be consumed, automation halt, so you reject, right? So the question is, should we accept or reject this string AA? The answer is we accept it, okay? So how do we accept? If there is a computation of the NFA that accepts the string, that is all the input string is processed and the automation is the accepting state in one choice of the computation, right? Okay, so that is a key idea. So for example, now you see, so there are two computation paths. One is this accept, another one is reject, right? So this computation, what happens to this computation? Frankly speaking, we ignore this computation. Okay, so we ignore this. Okay, that is a key idea. So rejection example, if the symbol is A only, I mean the string is only A, so you can clearly see that in each of the two choices, it will be a rejection case, right? Because input is consumed and you do not reach to the accepting state. Similarly here, it is not accepting state, right? So you reject this, okay? Another rejection example, AAA. What will happen in this case? Because A, input cannot be consumed. Something is still there on the tape, right? So this is a rejection case. I mean, in this path, another path is also rejection, right? So I hope you got the idea when to accept and when to reject in the case of NFA. So an NFA rejects a string if there is no computation of the NFA that accepts the string, right? So for each computation, all the input is consumed, number one condition, as similar to the DFA, and automation is a non-accepting state, then we basically reject the string. Okay, or the input cannot be consumed. In either of these two cases, we reject. Okay. So A is rejected by this and this both NFA. All possible computations lead to a rejection, as you saw that in this example. Triple A is also rejected by both of them. So what is the language of this? So basically, after doing some trial and error on this automata, you can find out that language accepted by this automata is AA. Okay, so very good. This was the first example. Now I am going to introduce what is known as lambda transition. Remember I told you lambda transitions provide delay in the computation. So basically the head is reading the symbol, right? And not moving to read the next symbol, but actually changing the state. Many times in the computation, you may require that actually, right? That kind of facility. Okay, I don't want to read the input further, but change the state and do something else, right? So in that, for this purpose, we have this lambda transition, okay, in between. So let me show you how to use this lambda transition. A is there. So read A. Now, head is not moving, but change the state, right? Automation change the state. Now you read next A and go to Q3. So accept. So A is accepted, right? With this lambda transition in between. This is a difference. This is not there in the DFA case, right? This lambda transition. Triple A. So now A, read head does not move. Then A, input is not consumed. So string A is rejected, right? These are very beautiful slides. I mean, it makes a lot of efforts to make these kind of things, right? But so language accepted by this automation is again AA. Now you see that this is also NFA accepting AA, and I showed you another example accepting. So you know there are two equivalent. So as I mentioned, just like in the case of DFA, in NFA also, for one language, there could be different possible NFAs. So your answer may be different with another answer if you do not copy. Right? So it will be different, right? Chat GPT से solve होगा ये? I don't know. So you try to find the answer. I think it's okay. Another example. So now there are two lambda transitions here. So look at, so alphabet is of course sigma is equal to a comma b. The string is a b. So what do you say? A b will be accepted or rejected? Any guess? Accepted. Very good. So you see, read A, read B, you accept, right? Very good. Now you see another string A B A B. What happens now? Accepted because of the lambda transition, right? You can again come back and so you are not reading anything until you change the state and again come back to thing, right? So this is a very beautiful thing. You see A B, go to here, use lambda transition, change the state, and then again read A B, accept. Okay. So you can now see the beauty of lambda transitions. It allows you more control, right, on the automation, right? So the language of this is, you can see that just like that AB, AB, you can also accept AB, 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 right? All these things you can. So essentially you can do AB plus. You remember this notation AB plus? Language, last class we talked about. So this is the language of this NFA. So I think now we have given you enough information. Probably we can go and talk about the formal definition of NFA. Mathematically, how do you describe it? So I think, yeah, you can look at this example here. I mean, I'm leaving it to you to verify that language is 01 star. What do you mean by 01 star? I will talk about it anyway. It's basically all strings with 10 10 10 combination, right? You can see the symbol here. Okay. If you look at language of this, if language is this empty language, this is NFA or DFA? NFA, because DFA has that condition for every A and all those kind of business, right? And here it accepts empty string because there was no accepting state. Here there is accepting state, right? So empty string will be accepted, right? The only thing. Both are true. So I'll show you an example where actually NFA is a little bit more complicated as compared to, sorry, DFA is more complicated as compared to NFA. Look at this. So NFAs are interesting because this is, if the language is this, singleton A, this is the NFA for it, right? And here you have all that condition for every symbol, there should be a transition and so on and so forth. So you have more states here, right? So that's why I hope I am able to convince you that NFAs are easy to design, more flexibility, more control. And DFA, you have more states sometime, right? Obviously, we would like to have less number of states if you want to solve a problem, right? Some language is given there, and you should know how to actually construct the DFA. The formal definition: Q is a set of states. Input alphabet, for example, something like A comma B, transition function delta, initial state, and set of accepting states, right? Now, little bit about transition function, how this looks like. In the DFA case, transition function was delta of Q comma A gives you some, so Q prime or something, right? Here actually, after reading one input, there will be set of states you will be getting because there are multiple choices, right? So here is an example. For example, you see here delta of Q01 is Q1, very good. What about delta of Q10? So Q10 you can get to Q0, and also Q10 you can get to Q2. So both of them are included, right? So essentially now transition function has a set. In the case of DFA, transition function was only single state. Read one symbol, You are in one state, move to another state. Here, in case of NFA, read one symbol, you are in one state, and output is multiple states, right? This is the key difference. What about Q naught delta? Q2, Q2 1, 5. There is no, transition. This is all possible in NFA, not in DFA. So then we can talk about extended functions similarly. Remember extended function, delta function is which operates on strings, right? Delta star operates on a string, delta operates on single symbol, right? So you have, for example, delta star Q naught A will be Q1, delta star Q naught AA will be Q4, Q5, right? One path is that, another path is that, right? Similarly, Q naught AB is Q2, Q3, Q naught, and so on. This is easy, right? So in general, when you are actually evaluating a string, you can decompose into smaller steps, right? In terms of delta. So delta star can be written in terms of delta, right? Yes. Here you need to look at the clever use of lambda. So Q naught AB, right? So Q naught AB will what? Of course, Q2 will be there. Q3 will be there because of lambda transition, right? And because of lambda transition, Q naught will be there. Okay. I know where you will be having problem. I can read your mind actually. Anyway, so basically, this is all trivial. You can all check. So language should be defined somewhere. Did I? Huh. So language of the NFA is all these strings such that delta star Q naught WM gives you bunch of states in which at least one of them is accepting state. Right. This is the formal definition of acceptance. Right. Now, I am going to show you that NFA can be converted into DFA. Of course, there is a whole strategic algorithm. Algorithm is given in the slides. You can read it at a cup of tea. What I am going to do, give you an example how it is done, right? The rest of things are straightforward. So, basically we say that one machine is equivalent to another machine if they accept the same language, right? So I am going to show you that. So we know that DFA accepts regular languages. I mean, whatever languages they accept, they are called as regular languages. Now I will show you that NFA also accepts regular languages. In other words, I will show that now you see that every DFA is a special case of NFA. NFA is much more general, right? So one part of subset is very clear. Whatever is accepted by this will be accepted by the other. We need to show the other part. In order to show the reverse part, I will show that every NFA can be converted into DFA. And we are done. That is a key idea. So here is, now you can see that for the same language, these two machines are equivalent. NFA and DFA. Obviously, you can see that DFA has more states. So this is the theorem. Language accepted by NFA is same thing as regular languages. So NFA and DFA have the same computational power except the same set of languages. Okay, so we need to show these two things. Languages accepted by NFA contains regular languages, and languages accepted by NFA are a subset of regular languages. Okay, these two equivalence you show, then you are done. Step 1, every DFA is trivially an NFA. That means any language accepted by DFA is also accepted by NFA. Okay, so that means one portion is clear, one subset is clear. Now to show the other part, I have to show that any NFA can be converted into an equivalent DFA. So that means any language L accepted by NFA is also accepted by DFA. Okay. So let me show you this beautiful construction of conversion between NFA to DFA. I'm sure I think some of you should have tried it at your home, but at least we will show you the Consider this NFA. So Q0, Q1, Q2, there are three states, one lambda transition, and the sigma alphabet is A comma B. There is one accepting state Q1, right? So what we do, we start with first start state, which is Q0, and I take, actually I look at the power set of it. So here actually simple Q0, I will write it as Q0, singleton Q0. It's just notational thing, right? And there is a start state. Because Q0 is a start state there, I am putting this as a start state, right? This is our beginning. I have to now construct DFA from this NFA. Now what I do, I look at Q0. So remember, in NFA, there is no need that for every symbol you should have a transition. But in case of DFA, we do require that condition, that for every input there should be a transition. So here there are two inputs, A and B. So I should know what to do every time I start. So let us start with Q0. What happens with if Q0 reads A? So from there I can see that if Q0 reads A, we get Q1. Q1 is a part of it, right? Also, because of lambda transition, we also can include Q2, right? So here I am making a new state Q1, Q2. From Q0, if you read A, we get Q1, Q2, right? Got up to this point, it is clear. Now what? So from Q0, I told you if I receive A, where to go. But what about B? If I receive B, so Q0, if you receive B, what will happen? In the NFA case, phi, right? So here I can just add one trap state phi. If you receive B, some trap state phi. Just okay, easy thing to do. Next, so the first state is taken care. Each input A comma B, I have told you what to do. Now I have to do the same thing for Q1, Q2. So Q1, I should tell if I receive A on Q1, Q2, what happens, and if I receive B on Q1, Q2, what happens, by reading the previous NFA. Now, actually, how do we do it? So first because there is only Q1, Q2 kind of thing, right? There is no Q1, Q1 comma Q2 here. So what do you do? On Q1, if you receive A, see what happens. On Q2, if you receive A, see what happens and take the union. Okay, that is the easy way to do, right? So what we do here, look at this. So on Q1, if you receive A, we get Q1, and because of lambda transition, Q2. And on Q2, if I receive A, so what will happen if you on Q2 you receive A? Null is phi, because there is nothing there. So now union of this is Q1, Q2. So basically, if I receive A, I will move it to Q1, Q2, right? Fairly straightforward thing to do. Now what? I should also tell you about B. I told you about A, but we should also talk about B. Again, we can calculate this in a similar manner. So you can see that if I receive B, so Q1 after receiving B in NFA, we get Q0, and on Q2, if I receive B, I get Q0 in NFA. So union is Q0. So just I take this and I can revert it back to Q0. Now, which state will be the accepting state? So I think one condition is satisfied. For each state, I have two inputs, right? For each input A and B, I know two transitions, right? That is taken care here. What about what is left? Accepting state. So their accepting state is Q1, which is subset here. So this we can make as a accepting state. So now essentially, I can call it capital A, capital B, capital C, and your automata is ready. DFA is ready, right? So this is the basic idea. Got the idea? So this is something fairly straightforward. Then after that, we have all. Yeah, so I think I'm sorry, I forgot that we also need here also, right? If you get A and B, what happens here? That portion is left. Okay, we need to add that last one. For each state in the DFA, we should know if I receive A or B, where to go, right? So that portion we need to add. Okay, so now this is the complete thing. Oh yeah, so accepting state is left. So this is the complete DFA, okay? Got it? So this is a very beautiful, simple thing. So somebody may ask you, take this NFA and give me a DFA, right? So you can actually do that easily now, okay? The basic algorithm is given here. General construction procedure, which I leave as an easy exercise for you. A T-type problem, right? So I leave it. Done. Okay. So next step, remember we are doing all this classification of Noam Chomsky, 1956, who gave this classification. There are 4 machines, 4 languages, and 4 grammar, right? 4 type of grammar. Now, I talked about finite state automata, especially DFA and NFA, and I talked about conversion, right? So every DFA is is an NFA automatically, and DFA can be converted into NFA. Sorry, NFA can be converted into DFA, right? That equivalence. Both of them accept regular languages. Now there are certain properties of regular languages which I am going to describe now. Okay. Again, thanks to Professor Bush. So for two regular languages, L1 and L2, their union is regular, concatenation is regular, star is regular, reversal is regular, complement is regular, intersection is regular. Now I think if you are at a very good university, I hope you are, then you can take a cup of tea and prove these statements. How will you prove it? You just need to find out a way to combine these DFA or NFA, right? If you actually combine DFA, it is a bit tedious. And since we know NFA is easy, so assume some NFA for L1, assume some NFA for L2, and then keep on doing some modifications to show all the properties. Okay, so let me show you that. It's kind of outline. It will give you an idea how these things are done. So we say that regular languages are closed under these operations, 1, 2, 3, 4, 5, 6 operations, right? So now you see that this NFA and this, basically, this is a very useful trick which I'm going to tell you. If this is an NFA, as I told you, I'm going to use NFA for these calculations. If this is an NFA with 2 accepting state, you can convert into a NFA with single accepting state by adding from these 2 accepting state lambda transitions to a final one. This is a useful trick. Okay. If there are multiple accepting states, that can be converged to single accepting state in the NFA. NFA है तो हम ये सब कर सकते हैं lambda lambda add करके, right? So it's easy thing. Okay. So this is the very important trick, and now we are going to use this trick quite often. Let me show you how. So in general, we have NFA. In between there is some blah blah blah, right? Start state and bunch of accepting state. Just add lambda transitions everywhere, and you can do this, right? Single accepting state. Extreme case. Suppose NFA without accepting state. So add an accepting state without transitions. This is extreme case. That is also okay. Because this is NFA. We can do all these things, right? Okay. Now take 2 languages, regular language L1 and L2. And suppose M1 and M2 are 2 NFAs with single accepting states, right? As you know, we can do that, right? And if there are multiple, I can convert it to single. We have this. Now what? So this is an example. This is the language A and B. This is BA. Okay. Union. If I have to take union, I take the start state from here and here, add lambda transition, and add another start state. This will become union, right? Simple. Because we are dealing with NFA, all these things are very easy. Otherwise, it's a bit tedious task. So union is done, and of course, this is the union, right? So only thing is that now there are two accepting states here. Concatenation, take the accepting state of M1, add lambda transition to the start state of M2. This is concatenation, right? Then this is an example here. Star operation. This is a little bit tricky, you see. We add a accepting state with lambda, start state with lambda, then these lambda. This will give you NFA for L1 star, right? So star operation. Reverse. Start, so reverse all the transitions, make initial state accepting state and vice versa, and you get the reverse. Okay. All these you can verify. Complement. Take the DFA that accepts L1, make accepting states non-final and vice versa. You get complement. This is the example. Intersection. So if two languages L1 and L2 are regular, we show that their intersection is regular. Then we use De Morgan's law. If L1 and L2 are regular, their complement is regular. You just saw their union is regular. And then the complement of the whole thing is regular, and which is nothing but the intersection. So intersection is regular, right? And this is all not needed. You can also skip that. So you see how quickly, because of these slides, I am able to finish many things. Huh? Okay, now I'm going to look at regular expressions. So remember, DFA or NFA means finite automata can be described by these machines, either DFA or NFA, or they can be described by languages, regular languages, or they can be described, of course, you saw the properties of regular languages. They can also be described with what is known as regular expressions. So I'm going to talk about regular expressions. It's not very difficult thing. I will give you a bunch of examples. That much is enough for you to have some basic understanding. We are not going anywhere deep. Okay, probably in future you will do this course on theory of computer science or mathematics of computer science or models of computation, whatever, you know. So again, thanks to Professor Bush. So here are the slides. So regular expressions are something like this. It's kind of shorthand. You see, if I write a plus b dot c star, that means a comma bc. This acts like union. Okay, a comma bc, and b and c are concatenation kind of thing, right? And the whole star. So star means all possible strings from this alphabet that are coming. Of course, the first one is lambda, which is the trivial case, and then you can write down, A, B, C, A, B, C, and so on, right? All those things will come, right? So this is a shorthand for, so this is known as regular expression, okay? So there is a recursive definition also. Primitive regular expressions, phi, lambda, alpha. Given regular expression R1, R2, there's, some concatenation, star, and this bracket, all of them are regular expressions actually. This is a very basic recursive definition. So now I'll show you some examples. The first one is regular expression, second one is not. So this is a very interesting question that can be asked in the exam. Show that this is not a regular expression. Or show that something. I'm giving you a paper also, right? So it's a tea time problem, right? So let me show you how to compute this. So now I will show you how this language is actually this, right? Let us see how step by step we calculate. So we use certain primitive definitions. Language of phi is phi. Language of lambda is singleton lambda. Language of A is singleton A. Okay, keeping these things in mind, and also these operations. Language of R1 plus R2 is language of R1 union language of R2. Language of R1 R2 is equal to language of R1 concatenation language of R2. Language of R1 star is equal to language of R1 whole bracket star. Language of bracket of R1 is equal to language of R1. Okay. Now take this example. A plus B, A star. If I give you this regular expression, I ask you to find the language. What you can do, language of A plus B dot A star is language of A plus B whole bracket language of A star from the previous expressions. It's nothing but language of A plus B, concatenation of language of A star. This is nothing but language of A union language of B, concatenation of language of A whole star. See all these operations I am using from the previous. This is nothing but language of A is singleton A, language of B is singleton B, so it's A union B, and then singleton A star. That means A comma B, and A star means all strings that are possible with A, lambda A, and so on. Now you can do the concatenation here, so you get the whole thing. Easy calculation. Given a regular expression, you should be able to find the language. Given the language, regular language, you should be able to find the regular expression. So questions that can be asked are very easy. I can give you one DFA or NFA, and I ask you find the regular expression. So from that DFA or NFA, you find out the language, and from that language, you find out the language regular expression. Some work is involved. Okay. So all those things are possible. So I think in the assignment 1, you will find many of these things. I think that's all about regular expression. So this one is shorthand for this language, right? And so on. You see, this is something like that. All strings containing substring 0, 0. So there in the beginning, there is some 0 or 1, and the end, there is some 0 or 1. Okay. These kind of shorthands are used quite often in models of computation. Okay. So this is like A star, B star, B means A is twice, right? A square, and because it will keep on increasing, and B2M for some different size, and ending is with B. This expression ensures that string ends with B, right? Everywhere. Right. So I think this is all string without substring 0, 0. These things you can verify. I think that's all. I'm not going to do anything else. Not required. So we have enough time. We can start something new. You can take some deep breath for a few minutes. थोड़ा ही करेंगे, ज़्यादा नहीं, just 10 minutes. Okay. So now you know most of the stuff about finite automata. So you are expert, I am assuming now, right? DFA, NFA, and so what we covered: DFA, language, regular language, DFA, regular language, regular expression, DFA and NFA to conversion to DFA, all those things. Now I'm going to look at, so one thing you might have observed that in this finite automata, we do not have any memory, just input, output, right? So this is something, it's a very low computing machine. By the way, one thing I should mention here, that for each of these, this slide is very, very important, and maybe you should take a picture of this and put in your brain. It's a very, very important slide. And I should tell you a few variations of this slide. For example, each machine has a language, each language has a grammar, right? So normally grammar has production rules, right? So English has a production rule and whatever language, right? So these languages also has production rules. And each of these language can be specified by its production rules. And when these production rules are used in sequential, then you get all these properties. But if you run them in parallel, you get systems such as L system, or basically they are used. So we got two new branches. One is algorithmic botany. So you can create these forests, trees, everything using these flowers, for example, using parallel productions of basically these production rules. So as I mentioned earlier also that Steve Jobs used these ideas to create Pixar, where they, for creating animations or the forest, actually you can, use these kind of production rules. So for example, if you observe a tree, there's a lot of symmetry there, right? So at certain distance, at certain angle, there is a branch, right? All these things you can capture with the form of these production rules, which are working in parallel on some alphabet. Okay, so these are really used in creating animations. So one branch is there. Another branch is algorithmic seashell. Seashell you might have seen near the ocean, right? So the surface of the seashell can be generated using these kind of beautiful things. So this is known as algorithmic seashell. You can find a book also, both on algorithmic botany and algorithmic seashell. Interesting stuff is available. Okay. So when we do production rules in parallel, in all these things, assumption is that production rules are which we use are sequential. I'm going to talk about briefly about those, how we use those rules to generate some grammars. Now, these machines are classical machines, basically based on, I would say, classical physics. You can assume that, but then there is a quantum version available also by Chris Automata, who gave me Christopher, who gave the quantum automata. So quantum finite state automata, quantum push-down automata, and quantum Turing machine. So these, so I'm just telling you as a summary, right? What you should remember. This is a summary of whole computer science. No matter which subject you study in computer science, this is a very, very fundamental thing, right? Even as you know that sometime you will see how even compiler can be constructed using some of these concepts. Okay, and this is really very important summary. And then there is a variation. This is a classical summary. Then there is a quantum version of it: quantum finite automata, quantum push-down automata, quantum Turing machine, and so on. And it is only after the discovery of quantum Turing machine in 1985, the quantum actually computing started really in a good shape. And finally, in 1994, a algorithm was discovered, which has, for example, factoring the integers. So RSA crypto system is in trouble because of quantum computers. Okay, so that is one thing. And the second thing is that uh, that this algorithm botany stuff, right? So these production rules can also be applied in parallel. So that's another branch. Okay, this much summary is enough for you. Okay, so now we are ready with PDA. Again, thanks to Professor Bush. Beautiful slides. I can actually, use them nicely. So there is a stack memory. Everything else is same. Input string, states, stack memory. So stack memory means push and pop. Right. आप लोग वैसे उसमें भी तो पढ़ रहे होगे ना कुछ डेटा स्ट्रक्चर्स एल्गोरिथम्स ये पढ़ा है स्टैक मेमोरी पढ़ा है so did anyone try have you tried this question that I gave you, that why we cannot find a DFA or NFA for the language A and BN? A and BN, we gave you that last time, right? So remember, in A and BN, that language A and BN, if you try to construct DFA or NFA, either you require infinite states, because we are looking at finite, so that is not a possibility, right? Or you require some sort of memory, then only it is possible. And that's why this stack memory is going to do the job for you. Another very interesting thing which I should tell you, that push down automata with single stack is of course PDA, but if you add another stack, it is equivalent to Turing machine. Though the Turing machine concept is totally different, but actually it is equivalent in terms of computing power, the same thing. मेरे को भी बहुत नींद आती है जब खाना खा के, वैसे मैं खाना खाता नहीं दोपहर को, right? So I think some people may feel sleepy. I can see. Anyway, we should have a cup of tea here, right? So we have a stack. We will not do much, but just briefly. We have a stack symbol, stack head. Bottom symbol appears at time 0. Okay, so how do we do the state change here? We are in the state Q1. After input symbol A, from the stack, you pop this and push C. Pop B, and push C. on the stack, and you change state from one state to the other state. This is a typical scenario of push-down automata states. Let's look at this. The stack is having BHE dollar. So it says that read A, you read A from the other tape, pop B. So B is there in the top, you pop it, and then push C on the top. So you can see that C is there, right? So here it is like this, push, pop. Here, so this is B is replaced with C actually. If you have this A lambda C, so you don't have to pop anything. Lambda means you don't have to pop anything, but just push C on the top. You can see that at the top of B, from there we have C now, right? Just read the symbol at the top, right? What is happening? Similarly, we have AB lambda. So you pop B and push nothing, right? So we have this. A lambda lambda. Nothing to push, nothing to pop, nothing to push. So you are no change. बस इतना ही करते हैं, ठीक है? I hope थोड़ा सा मैंने push दे दिया ना. So probably some people who are very enthusiastic, they will read on their own. That happens. By the way, final thing I would like to say that as I mentioned, there are two very good books. One is Michael Sipser, which is from MIT Press. Some people find it difficult. So you can read another very good book if you are reading. So let me show you that book by Motwani. Ulaman, this is the book. It's a very nice book. Introduction to Automata Theory, Languages and Computation. Each of you should have this copy on your table if you are serious about computer science. And I think since this is an opportunity, you can look at some of the stuff here. Oh, ये तो hard cover 25,000 का है, right? But Indian edition is very cheap actually, just 500, maybe 600. Okay. So Hofcroft, Ulaman, and Rajiv Motwani. I think, as I mentioned earlier, also Rajiv Motwani was the advisor to these Google people, right? I mean, he gave the first check. So, okay, it's a very important book. If you really want to really understand computer science, you don't have to go to competitive programming. You have to read this book. There are two books which are important. One is this, Automata Theory. You should understand. Number one, for serious computer science. Number two, Donald Knuth, Art of Computer Programming. अगर ये किताबें दो नहीं पढ़ी हैं कंप्यूटर साइंस की, ये एजुकेशन अधूरी है, राइट? फिर लिख लो वर्ड्स, आज के 10 साल के बाद भी याद करोगे, because people do contact me. Those who have read, they enjoy the beauty. Those who have not read, they are still struggling. ये बहुत इंपॉर्टेंट किताब है, you should read it. दोनों, आर्ट ऑफ कंप्यूटर प्रोग्रामिंग. बहुतों को समझ में नहीं आएगी. समझ में नहीं आएगी तो यही तो तपस्या करनी है तुम्हें ना, to uplift your brain. Right. Okay. So I think that's all. Any question about the exam or anything? It's okay. Done? So 4 questions. I think you should have a cup of tea here also. In US, we used to allow this thing, but here I don't know. So there actually people come with newspaper and a cup of coffee, sitting there enjoying the lecture. Here it's all, no tea, nothing. Anyway. Thanks.